راح من سيليكون فيجن لجودكس، فهيز ريلي دوينج ويل، وان اوف ذا فيو اكسبرتس ان كاد فلو في مصر. يعني انا احب ارحب باحمد جدا، وهسيب سلمى بقى you should introduce him more properly بقى بالتفاصيل.
تمام، شكرا يا دكتور.
شكرا يا دكتور.
Engineer Ahmed received his bachelor degree from VLSI in nanotechnology and nanoelectronics engineering, and then he started working in the CND at AEC as a contractor with Helic, a reputable EDA company based in California. And during his time in the CND, he started pursuing his master's degree at AEC from Electronics and Communication Engineering Department, and he completed it by 2021. And by the end of 2020, he joined SciVision as a CAD engineer, where he got promoted to senior CAD engineer after only 1 year. And in April 2022, he joined Goodix. He's currently leading all the CAD activities within this company. We are welcoming you, Engineer Ahmed, and you can start your own presentation.
Okay, thank you, Salma. Share my screen. So, do you see my screen now?
Yes.
Yes.
Okay, it's a presentation or like
Presentation.
Okay, thank you. Okay, so how are you, everybody? Hope you find this presentation interesting and useful. So I will take you in a journey in the process design kits, how they evolved, what are the main components, and so on. So as you know, in the IC industry nowadays, processes, tools, and requirements all come together in a well-established design flow. These mature design flows that we do nowadays are supported by the process design kit, shorted by PDK. So the PDK is the element that bridges the gap between the design teams and the fabrication foundries. Or we can also say that it is the link between the design, that's like logic and simulations, and the physical semiconductors or silicon wafers. So our agenda today is the rise of BDKs, how we reached to have like a well-defined BDKs, what are the main BDK components. Probably we will spend most of the time in this part. We will have an example of a BDK. It's of course an open source BDK, so we'll see. But it gives like a good illustration for like a typical or real BDK. Also, I will list some advanced checks that we need in the modern BDKs due to the advanced technologies and small nodes. I will talk about standard cells. Another important issue that we always need to stress is foundry information security, because it may cause a lot of trouble if you are not aware of it. Then I will show you some open BDKs that you can use to learn or just try things or play with. Okay, so first semiconductor companies like in 70s or 60s or so, they were all owned their fabrication facilities. They had their foundries. The design and the production were both in what they call in-house. However, as with any fabrication facility, if you are just working with one customer, you will have times that you do not have production because you don't need all the production. To keep production going, the semiconductor companies started selling their manufacturing capacity to other companies, which produced the model that we know nowadays as fabless design companies. So because fabless, I think if you follow the previous presentation of Dr. Sharif Hamouda, he talked about that, about the distinction between a foundry and a fabless design house and so on. Then in 1987, TSMC was founded as what's called a pure play foundry, which means a company that only manufactured ICs for other companies. They do not manufacture ICs for themselves, or they do not do the design process. They are just responsible for fabrication. So with the arrival of TSMC into the ground, the cost and the risk of entering semiconductor business was no longer a burden, or it was easy for a small company to enter the IC design, because the major issue or the biggest cost during the cycle is for fabrication. So we now have someone who is specialized for fabrication and can also produce some tape outs efficiently. Before that, before this model of pure play foundries and fabless design, what was actually happening during an IC design process? All the IC design was tightly tied to the fabrication step. So as a designer, I was concerned from I was concerned in the design state, in the simulation, I was concerned about semiconductors and how it will be fabricated. Because every aspect of the design was modeled at first principles. With each transistor and the device was characterized by computer-aided designs, the TCAD ones, which is the numerical simulations that that combines the process of device and circuit simulation and modeling. So the challenge was huge, because TCAD simulations are very heavy, and you cannot simulate like a big design using TCAD. Okay. So here comes the rule of SPICE. Invention of SPICE was a great breakthrough that enabled fabless companies to continue innovation without the heavy burden of the semiconductor level devices simulation. Okay, so we expect, of course, that the SPICE models will be like an integral part of our PDKs. I will talk about SPICE and models provided by Foundry in some details. Okay, so a PDK is a set of files provided by Foundry, of course. Each PDK acts as a link between the design. Each component actually acts as a link between the design and its physical structure after the tape out process. So as we progress through this presentation, each PDK component will be revealed one by one. So I hope you find this method to be like interesting and enjoyable. Okay, first, so SPICE model. As I said, the key breakthrough in solving the mystery of heavy TCAD simulations was the SPICE with its concept of abstraction. So the presence of device models and the SPICE simulator made it useful to use a pre-characterized device components that could be simulated together as a system in a much more reasonable time. This enabled us to separate the fabrication and characterization from the design process, which in turn enabled the creation of complex designs based on more components. So manufacturing no longer is done in-house. A designer can now take advantage of pre and well-defined and characterized devices and already tested and known to be successfully fabricated by a foundry. And then he takes it quickly and easily and add some editings in several ways. This is the design process to produce a complex structure. So the design world's focus shifted from trying to build like good transistors to trying to build better systems and applications that are built or assembled from existing transistors, which is, I think, is the most important factor in the Moore's law revolution. So, SPICE itself was invented in UC Berkeley as the first EDA tool to make analog simulations. Then it was spun off to from the several commercial tools like Synopsys HSpice and Cadence. And it has the old BSpice. But for SPICE to be able to simulate a transistor, it needs equations that governs its behavior. Here comes a compact model job, which is the BSEM models. It's a mathematical model that combines electromagnetics, device physics, also maybe quantum physics and like the advanced nodes, 3 nano and so, to predict the electrical behavior of the device. So BSEM also created, BSEM I think it stands for Berkeley SEM, so it was also initiated in Berkeley. It was one of the first compact models, and it's currently the standard for all foundries. It has, as you see, several generations. So when somebody creates a new type of MOSFETs, like multi-gate MOSFETs, first it was like the planar one normally used. Now they are multi-gate, gate-all-around, FinFETs, and so. So they create models for it. The model is something like this. It's in reality, it's much more complex indeed. Probably if you have taken a semiconductor physics course or devices course, you will have seen something like this. So where is the BDK and all of that? BDK doesn't give us the BSEM or the compact device models. The BDK just gives us the model parameters through the model files. So the model files are just some parameters that are already known inside the model, but they need to be reflecting what's happening in the foundry process. So me as a foundry, I decide that I will use BSEM model like BSEM, for example, BSEM MG, and I will decide on the level of the simulation. Level is like for each level in the model, you have more extra parameters and an extra quantities that you can play with to change the behavior. Okay, so what actually is given in the BDK, as I said, is like the model files are contains just the parameters, not the compact model. I have an example here of a model file. Okay, so I repeat, this is all from like open BDK and so, because I cannot share something that's really industrial. So this is the model for a BFET. Its type is PMOS, level 72, and all these are like parameters that was characterized and extracted by the foundry, and then it's provided in the file. Okay, so the simulator will take simulator already, the industrial simulator already knows the compact model, and then it will look for the value of the coefficient or parameters from this file. So first element we have here that we will add to our BDK is the model files, which will be used by Spectre, Spice, or Eldo, the widely used commercial simulators. Okay, so just because we know that devices are working and we have models for it, that doesn't mean that they will be connected in any way and then will be successful or manufacturable at the end. The completed design, it will certainly react to the fabrication process, like lithography effects, chemical, mechanical polishing, contamination, process variations. All of that will affect the functionality, performance, yield, and everything. So foundries needs to find a way to assure the designers that their design would actually work after tape out. Okay, so the first answer was the introduction of design rules and their checks. So the design rule defines the fabrication requirements of a particular process at a given foundry, of course. So design rule checks were used to confirm that a design satisfied minimal constraints of geometry and to help user determine which drawn layers represented which masks and so. So if you know the concept of layer mapping, that the GDSs always have only numbers, but we have layer names, so we always have a layer map combining almost every physical design tool. We need a layer mapping file to tell the tool that the GDS number that you find actually corresponds to the layer with name metal 1, for example. Okay, the checks will be implemented, of course, by a tool. So here comes the role of physical verification tools. Mostly known, of course, is Caliber. Also ICV, of course, is from Synopsys, there's a physical verification tool, and we have from Cadence, Assura, and PVS. These tools are responsible to run software that could automatically scan the layout and find different configurations that violates the rule. So the input for a physical verification tool is simple, just your GDS and a set of rules, which is, we have an example for this rules here. Of course, the rules will be provided in the BDK by the foundry. Actually, the syntax of the rules is pretty straightforward, and sometimes you can develop your own verifications and checks. So this is a typical syntax. In the start, it defines the physical layers that NOL corresponds to GDS layer number 3, and so. Then we have layer derivations. Layer derivations will produce for us what's called CAD layers or logic layers, because those layers are not physical layers. They are not actually in the design. They are just something we made to simplify the rules. It comes out from the manipulation of two or more other layers, like NOL and BWell. Taking a Boolean OR between them will give us layer well. The same with gate. So rule section. So actually, well 1, this is from here is a rule. Well 2 is a rule. This all follows the standard SVRF format, standard verification rule format, which is used only by Caliber tools. So the syntax is simple. So here, this is a comment, or this is the message that you will get if you actually have this violation. So this violation gives a 1 when if we have NOL and PWell and they are intersecting, because we are doing an AND operation. So for example, if this is NOL and this is PWell, so the ANDing operation will give us this the place where they intersect. So this value will not be 0. So we will have this check. This will be a DRC violation. Okay. So for the early BDKs, the combination of these two elements, the pre-characterized device models and the DRC, the design rules, became the first minimal requirements for fabless design. So me as a person, not related with foundry, I just have the device models and the DRC. I can actually theoretically, nowadays, this is of course impossible with just these two, but theoretically, I can tape out a design. Requirements for these were the first things that we refer as BDKs, of course. Okay, so more physical verification. Over the time, the content of BDKs had to expand significantly because processes targeted continually smaller and smaller geometries. The fabrication process began to be affected by issues that we may seem trivial, because, for example, this LVS, the designs were small, so it was easy to make sure that the circuit we are layouting actually compares, and we didn't need the tool actually reflects the actual design. So after, when the designs get more complex, no, we needed the LVS, layout versus schematic checks. It's a comparison that verifies that a physical layout actually, in fact, implements the required circuitry. So LVS flow for non-users or non-experts feels like it is something complex or tricky, but actually it's very simple. What happens by the tool is it works separately on the layout and the schematic. First, on the layout, it has like certain configuration which is in the rule files to extract the devices. So it has rules for example, a transistor. If you find like an active area intersecting with a poly, then this will be a transistor. Okay. Also connectivity through some statements that connects that lets the tool know that which layers are connected to which other layers. So it will produce a layout netlist. Okay, which actually can be can view it in a text file. It's very similar to the schematic netlist that's produced from the schematic. At the same time, it produces a schematic netlist, which is probably in the CDL, circuit description language, as a description of the schematic. Then a simple comparison between both netlists will give us the verification results. Okay, so occurred like extra revolution or extra complexity to the designs. So we needed extra amounts of metals, and we needed to connect the circuits and the components in different complex ways. Okay. And also the metals themselves and the interconnects can no longer be assumed that they are an ideal conductor. So we have like something called parasitic effects, which is unintended electrical currents had to be identified, and we have to know its effect on the circuit. So this happens by parasitic extraction. So for example, here we have like a bunch of metals. We will have capacitance between metal 1 and metal 2, metal 1 and metal 3, metal 2 and itself. So we'll have a lot of combinations to have a parasitic capacitance. Also parasitic resistance from the the conductors themselves, because they are not ideal conductors. So parasitic extraction tools have two main paradigms. So we have rule-based and we have field solvers. Okay. What's the approach of each one? The first one is we will talk of field solver. So it just needs the layout and the process specification. What is the process specification? It's a file with different format from EDA tool to other, but it's somehow standard. It's just, let's open it. It's just a listing of the physical properties of each layer. So this is a MIPT file. This is a format that's used by Calibre. If we go like here, we'll find it has like substrate layer called SI sub, and it gives you the thickness. It's Z direction bottom, Z top. So it has all the info about the Z direction. So the height, because we as a designers, we will not edit anything in as you know, in the vertical direction. So it gives us the thicknesses and the resistivity, permittivity, and so on. And it has like here called this layer, it will be a diffusion with a minimum width of such and such. Okay. So what will happen with this file is that we have it will be given for the parasitic extraction tool with the layout, and it will solve Maxwell equations for this design. Also, there are a lot of variations of how they solve the Maxwell equation, but typically they have methods to solve it and give you the final extracted netlist to simulate with your design. Second approach, of course, the first approach is not applicable to big designs, impossible for full chips, because it is very computationally intensive, because you need to make a lot of meshing and so. So maximum they are used in like high frequency RF blocks for only a small block. But if we go to that other approach, we have an extra step called the model calibration, where it actually takes the process file and creates another file, which is the rules file. So if we open this file, you will find here it is generated by Xcalibrate. This is a mentor tool that took the MIPT file and produced us the rules file. What are the rules file? It is like a rules. If you go deeply through it, you will find it is like it's like a lookup table for patterns inside the layout. So the tool takes the design and looks for some patterns and decides which value will be suitable for that, which R and C value will be suitable for that pattern or that geometry structure. And it produces the final extracted netlist based on that. Of course, this approach is not accurate, but it is efficient in case of digital flows, low frequency, and indeed can extract a completed chip at once. Okay, so previously we said that we have DRC, but now we have physical verification rules. They are actually organized in what we call run sets or rule decks. So this is a major part of a BDK, the physical verification rules, DRC, LVS, PIX, and some other advanced rules that were we will discuss briefly, but they were forced to get into the design flow due to the advancements in technology nodes and the extra restrictions. Another part is TechLab and Tech Library and PCell will be provided in the BDK. TechLab is provided by Foundry to enable the normal schematic and the layout generation. So this is the tech-lib provided by foundry. You have MOSes here. So you will find you have a layout view, and below will be a schematic. There will be a symbol here. So you can add symbols to schematic and place layout in your design. Of course, each B cell contains several parameters that can be modified by the user according to its needs, and also it will be finally linked to a certain model. So this is the B cell of the NMOS transistor. You will have a parameter that links it to the correct model, so that the simulator can acquire its correct parameters. Also, another interesting concept is the B cells of the layout. So actually, you will find that the layout itself changes automatically according to like the number of fingers you create in the schematic. This is because this is not an actual layout. It is B cells is just a bunch of code. In Cadence, it's scale code. I think in Synopsys tools, it's Python. So it's just a code that generates the layout view on invocation. So when you open the view, it takes the parameters that you put to the cell and generates the layout, the proper layout for it. Okay, last but not least, of course, is the documentation, because documentation is necessary for all the design steps. So the main, of course, you will find in a real BDK there is a lot of documents that that covers every aspect of the process. But the main and the most important one is the DRM, of course. It's a user-friendly representation of the process requirements. Release notes, what's happening in the new releases, what happened over the previous release. Did we add a new check? Did we enhance a certain model? Also, some usage guides for models, how to use them, how to implement the verification rules, how to set up the BDK, and so on. So these are the main, as I see, the main components of a BDK, like a traditional BDK, without the need of extra checks that is necessary for the sub 20 nanometer nodes, for example. So I have one here installed. Let's look at its hierarchy. Okay. So this free BDK I downloaded. I have the links in the last slide. I downloaded from North Carolina State University, I believe. So this is the typical structure. So it seems they are only working with Calibre, but for other real foundry BDKs, you will find this is a directory called verification dex, for example, and you will find files for Calibre and other verification tools. So let's go with it. If we open Calibre, we'll find here the Calibre DRC rules, LVS specs, and some include layer. And this is the MIBT, I believe, that we also showed, that contains the process specifications. If we go back again, we have CDS lib. So when you see the term CDS and IC design, no, it's probably something for Cadence. So this is something to work in Cadence, and it will be the tech lib and some setup scripts for, I think build is just something internal inside this BDK. But the setup scripts, you need some setup scripts to initialize your environment, define the colors of the layers. We have a file called the display.drf. This is the ones that controls the shapes of the metals and the environment and so. And you have other files that control your experience with the Cadence tool Virtuoso especially. Okay. And here the skill, mostly you can find some skill scripts, but mostly they are skill callbacks. What are the skill callbacks? It is some functions that when you do a change into the schematic, they can be triggered automatically, like change the value of the length of the resistor. So it will trigger a callback that calculates for you the value of the resistance, for example. So these skill callbacks go hand in hand with the P cells, of course. We have a directory for the doc. Here it's not the rich typical design docs. It's just release note because it's an open BDK, but or in the usual cases, you'll find a lot of PDF files. Sometimes they are encrypted. Sometimes they are complex to read. Maybe it is by intention, but you will find a lot of BDK, of DRMs and the usage files for your BDK. Lastly, our HSpice here are the model files. Also, they will be in a real BDK. They will be several model files, and they will be categorized according to several things like low V threshold devices, low leakage devices, or also according to process corners, fast, slow, and typical, and so. Okay. So more advanced checks that were necessary by the modern, they were needed by the modern process flows, especially the sub 20 nanometer nodes. So we had to, after scaling and the increasing demand for more functionality contained in a single chip, this gives a huge challenges in terms of yield and fabrication and so on. So to address these challenges, we needed to implement solutions to have like augmented or enhanced DFM. DFM stands for Design for Manufacturability. These are automated to let the designers reduce the impact of variability of the process flow and improve the yield of their designs. So the DFM, you can go to here. You will find like several checks, like something called layout lithography process checking, CMB process compensation, which is tells you be careful if you are in these coordinates inside the wafer. Be careful, you will be etched. You will be etched extra because this area is hot area for the CMB process. Something like that. Also, pattern matching from the patterns. It will give you some insight about the yield of your circuit. Electrostatic discharge. Also, the ESD is actually maybe you can get a ESD charge, not like the issue of ESD. You will not feel it after tape out. It's a reliability issue. Maybe you can feel it after some time. So it's important to do the ESD checks and put the protection circuits. Currently, the multi-patterning issue also. So we will, if you are working in advanced nodes, you will hear that design is colored, the design is colorless. We need to add coloring. And so why we need that coloring? And so this is due to that we reached the UV lithography resolution limit. So if we have some features on, for example, metal 3. So if in the normal cases, metal 3 will be just one mask, but that one mask cannot cannot like make the lithography for small features. So we had to separate it to several masks to implement smaller features. That's the colors. So you will have M1 color 1, M1 color 2, M1 color 3. This is what's called multi-patterning, and this is needed. This is very common in the sub 20 nanometer nodes. Standard cells. Actually, there is a misconception that standard cells is part of BDK. It's not that. It's not actually a part of BDK, because standard cells are like IPs. So foundries, maybe foundries, sometimes maybe a foundry can produce them, but they are foundries or a third-party design houses can provide different IPs, okay, based on a certain foundry BDK, of course. So what is a standard cells? It is like a pre-characterized, designed, characterized, and everything, a small design, usually a digital block, logic gate, or other. It's shipped with complete info about schematic and layout, and can be placed directly, manually, I mean, in analog flows, or by BNR tools in digital flows. So a standard cell library contains the library database, which is the library cell view, timing info for the timing tools like prime time and so, GDSs of the cell, lif files, which give us abstract flow of the cell, its dimensions, where is the pins and the antenna info, and so that it provides the insight for the place and route tool, Verilog and HDL models. Sometimes also they come with already generated parasitic netlists. Also, I found there is a open source standard cell that's actually very big and have a lot of variations included in that link. So you can also check it. Okay, an important point that we always have to stress is the foundry information security. Due to the fierce competition between foundries, foundries consider info related to their processes as a trade secret. Also, you will not be able to access any foundry-related data without signing an NDA. Legal actions can be taken, so be careful not to violate any terms of NDA, or you may threaten your career and sometimes even your organization's business. So this is a very critical point. Okay, so you can find links for open BDKs like Google Sky Water. This is recently BDK that's completely developed and have the source on GitHub. They aim to give us an open source BDK, which will be first time, I think, in IC industry to be to take the paradigm from software. So software always have a lot of open source things, but in IC industry we don't have anything open source. So if this succeeds, I do not know if it is actually successful or not. But it will be something huge. If this is successful, it will be a great leap in the future of IC design. Cadence provides high quality BDKs called GBDKs. I think for 180, 45, and they have a new advanced BDKs for imitates the FinFET technologies. So you can download it freely. If your university or company have any company subscription, you can just download it from the Cadence support site. The North Carolina State University set of open BDKs, this is the one that I adopted and showed you in this presentation. Okay, thank you for your attention. Hope you enjoyed the session, and I'm open to any questions.
Thank you so much, Engineer Ahmed. We have only one question.
Okay.
Yeah, sure.
We cannot see your presentation, Ahmed. It's
What?
gone. We cannot see your presentation. It's gone.
Because I'm looking for Zoom. I want to see the question.
I see.
Where is the chat?
Yeah.
Yes.
I'm checking the form now.
So this
Someone is asking, they are filling the form for a question. So
okay.
someone is asking why there is no actual BDK for educational purposes.
Where is that?
They are filling forms, not in the chat, but I can send them in the chat.
Can we allow them to? We have 15 minutes. Can we allow them to speak? You know, Salma. Or is that
they
too hard?
they can send the question in the chat. Because,
Okay.
so let me see.
Okay. So I think I can answer these questions. I see them from Ziad Muhammad Salah. Do the graduation project is a must to get a job in IC design? For me, my graduation project was not so close to what I'm doing. It was something purely digital and ASIC flow and so, but I got into EDA and CAD thanks to Dr. Yahya Ismail, of course. But I do not think it is a must. If you have the skills, just get an interview, and I'm sure you will get something good. And good luck anyway.
We are maybe Ahmed. I should tell them we are working with some Intel advanced PDK for AUC, and I'm working hard on it, like 14 nanometers. So if that happens, we should have a lot of infrastructure at AUC for such design projects before you graduate, hopefully.
Yeah, that will be great for students and researchers. You have open access to Intel.
And I intend to open it to Ain Shams, Cairo, and everyone else, but hosted at AUC. So in case someone is sitting from there, you know.
Great. I think that's great news. From Muhammad Saeed, we are in the process of gaining the required skills for a very trendy topic concerning our graduation project. It has digital IC design, mainly FPGA plus machine learning and mobile networks, optimization technology. The question: how do we get the best mentorship sponsorship available? What are the required skills and steps towards getting the sponsorship? You are asking about a sponsorship from a company, right? So I think you can try to reach people working in digital design teams on LinkedIn. You have a lot of IC design companies now. All the people can be easily contacted from LinkedIn. You have Goodix, you have SideVision, you have a lot of other companies. So just contact him. If you don't have a contact through your university, through a professor, or even someone who is doing a master's or doing a master's and he's working in industry or so, you can always do LinkedIn. And of course, best of luck. Muhammad Mahmoud, I asked what the requirements to enter the CAD field. Okay, requirements to enter the CAD field. You have like the knowledge of IC design flow, an overall knowledge. You don't need to be an expert in analog or expert in layout or expert in digital design. You have to know what is the flow in each one of them. What do the people do? What are the tools needed? You should also have a strong programming skill. And it's the most important thing I see is the curiosity and the ability to search and get to search for info and self-learn, because you will not have a lot of resources because CAD engineers are not we don't have a lot of now big numbers of CAD engineers, so you need to be able to self-learn. Okay, and if you are a fast learner, that's a big advantage. Okay. Why most of the free BDKs contain a lot of errors like CBDK? Okay, CBDK is a Synopsys educational kit. Of course, free BDKs will have a lot of errors because they are not maintained well. Because like because people do not assign it resources or like the importance, because they will not be at the end, they will not be going to a foundry and taped out. So people are working for like educational purposes. And actually errors during learning is something good. So you will learn from the errors. So I think I see this as advantage, not that disadvantage. NDA, can you repeat why it's not good? No, NDA is good, but if you sign an NDA, you have to follow it. And non-disclosure agreements are like contracts that says you cannot tell anybody anything about the info you are seeing inside the foundry. So it's good. It protects the foundry info and so, but you just have to abide with it and be careful. There is open internship. Actually, you mean in Goodix? I'm not sure. You can contact me on LinkedIn. I will ask ask the teams, HR, and everybody if we can have one. Is there an expected time to have an access to the open source BDK? If you mean the North Carolina state, it's like 10 minutes. They take from you your email address, and 10 minutes you will find a link that has been sent to your email with links to all their open BDKs. What is the exact rule of CAD engineering companies if Foundry provides the BDKs with complete files? Okay, the first rule is how you will integrate those files in with the designers in their design flow. So how you will set up the project. It's called the CAD setup. So who will make that CAD setup to enable the designers to do their jobs. Also, you will have always the files from Foundry are not like are not Bible. So you may have issues. You may have to return to Foundry. You may have to get those files from Foundry. You are responsible for downloading them, and so. What's your expectations for the field in the next 5 years? The IC design field in Egypt, I see that it's expanding and it's going very well. We have a lot of companies in the recent years, and multinational companies opening and expanding. So the vision I see is very optimistic. Where I can find start internship in Egypt, I am not a fresh graduate. I have a good academic knowledge. I think internships are announced by companies from time to time. Also, as I told someone before here, you can, if you are interested in a certain company, try to reach people on LinkedIn. It's never hurts. What are the most promising topics in the industry to put a potential in it or to make master in it? All topics are interesting. Everything is prospering. Analog design, analog layout, digital design, digital PNR, everything's good. So anything like CAD, if you like, of course. So any step in the IC design, I believe it will be beneficial for you. Sorry, I mean that PDK to Cairo Uni. Ahmed Zaid, yes, before. Oh, you are asking about the PDK that Dr. Yahya was talking about. No, I think Dr. Yahya is here. I don't know if we have.
Well, I mean, I'm hoping over the summer. So I'm hoping this fall it should be available. Cross your fingers. So we're doing our best to fund it and get things going with Intel and so on. Okay. Inshallah.
Inshallah. For undergrad students, how to practice for digital backend track? Is there any source that provides idea for projects where specs of timing, area, power are required to have challenges achieving it in PNR, and what are the expected skills in undergraduate until? Actually, I'm not. I don't work in the digital backend track. I will not have enough info for this question. But try to reach someone who is expert for in digital PNR. You'll find there are a lot. That is just search on LinkedIn. You'll find a lot of teams in Egypt working digital PNR. Okay. Thank you.
I'd like to announce one thing. We have a talk on Monday. That you're all invited. It's face to face. We have E.B. Friedman. E.B. Friedman is one of the most famous people in the world in VLSI design and electronics design. You're all welcome to come, including people from outside, but we have to organize it. You have to have your vaccination and we'll allow you in. But you should expect a great talk. And AUC students got an email, but it's this Monday at 3:30. At PO19, which is a conference zone, okay? And you're all very highly encouraged to attend, okay? Thank you. Thank you, Ahmed. Great job.
Yeah, thank you, Dr. Yahya. Thank you, Salma. Thank you, Halim, for organizing this event. Really appreciating inviting me. Thank you.
And thank you, Salma, and everyone, Halim, for the organization. Yeah.
Thank you.
Bye-bye. Great event, by the way. Good job.
Thank you, Dr. Yahya. Goodbye.
Yeah. Bye-bye. Bye-bye, Ahmed.
Bye.
I'll come to you.